Are we on? Yes. Okay. Welcome. This talk's going to be about streams in Java 8. So how many people have used streams, Java 8, lambda? I've obviously used it. So not so many. I'm going to give a brief, very gentle introduction, then start ramping it up and ramping it up. So I'm going to mostly sit down because I can't stand and code at the same time and type. And also, if you see me make any mistakes, please shout out and help me debug my own stuff. Before I get started, there's this stuff, but you don't really need to read it. You just got to know that you don't place any bets on what I say, please. That's it. So some of the goals of this presentation. So Java SE8 introduces something called lambda expressions. And among one of the benefits of these, it's going to enable better APIs, better libraries. And hopefully what I show you here, you can learn how to apply what you see in streams, the techniques there to your own libraries as well. And understand how streams actually work and how to get the best out of them. And an important point, this is the first of many optimizations we can potentially make. So we're coming out the gate with something pretty good, reasonably optimal, but we can do a lot more under the covers as we go forward into the future, which I think is really exciting. So if you look at code out there, how many people have written like spaghetti code doing for loops over lists and maps and all sorts of stuff like that with a whole bunch of garbage variables and all this stuff, and you look at this great spaghetti mess and you go, ugh, it's horrible. Well, that's traditionally how we do stuff in Java. We all do for loops over collections and iterate over map entries and stuff like that. So we've coded over loops. But it's really very sequential, and it's frustratingly imperative. So the answer we have for Java SE8 is a stream API with a little help from lambdas. So what is a stream? It's essentially an abstraction for specifying aggregate computation. It's not a data structure. It's essentially a view over your data. And it can be infinite, for example. It essentially ups the levels of your abstraction. And that if we up the level of abstraction, we essentially have a lot more space underneath the covers to do all sorts of optimizations and monkeying around with what goes on. And that gives us the ability to do stuff like fusing laziness and something called going parallelism, or map reducing the small, which I'll talk about. So this API is the first of what I hope is many good kinds of stream-like APIs in Java SE8 and beyond. It has a particular model for doing sequential and parallel computation, but it's not the only model. You'll see other types of stream-like abstractions going on. You'll see stuff from like in Play and Akka. They can all use these Java 8 features too. RxJava, for example, is another stream-like API. They can all take advantage of these same concepts and patterns. So it's like these functional patterns are quite interesting and quite important, and there's a gentle push in Java 8 to a more functional style if you choose to go in that direction. So you'll see stuff like map, filter, flat map, reduce. These are common patterns you'll see across all sorts of APIs. Okay, so let's get a bit more into some stream code. And I'll switch to an IDE instead. If I can actually switch to, where's my IDE gone? There we go. So I'm using IntelliJ, but you can use Eclipse or you can use NetBeans. Choose your poison. Everyone has their own idiosyncrasies about what's their favorite IDE. Mine's IntelliJ. Most of them have good Java, they all have good Java SE8 support. So another thing to take away is if you can choose an IDE, download SE8 and start having a play with code. Just get a feel for it, have a play. And hopefully, what I do here will encourage you to do the same. So here's a really simple, very, very simple example of looping over some words in a list. List is a word here. I'm not saying how it's created, but there's a list of string for words here. And I'm just looping over this. It's very, very simple. Just loop over the words. If a word is greater than 4 characters, count it up. Yeah, it's very imperative. So this, if you notice, this conflates what with how. It's saying we're filtering and counting, but we're also mixing it up with the style of iteration we're doing with a for loop there. It's not particularly complicated, but how would we do that with streams? So we want our words again. Like so, that will return a list. And now we have some new methods on list. called stream. That creates the view over which we operate over the data. So that's a new method on list. Is list an interface or an abstract class? What is it? An interface, and we added a new method to an interface. How did we do that? Well, if you went to Venkat's talk, I think, you might know the answer already, but if we just have a quick look, we can add code to interfaces with default methods. If you want to integrate into the Streams API, have a look at these methods and see how they're done and copy them. So there's a new default method we've added to list and collection and so forth like that, so we can get a stream view over our list. And once we've got a stream, we can start doing operations on that. So we can start doing a filter operation. We want to filter all our words and remove all the words less than 5 characters. So essentially we can copy this piece of, for some reason my shortcut keys aren't working very well, and we can create lambda like so. Just copy the snippet of code we saw before and plonk it in as a lambda, as a filter, and that will filter like so. And then what we can do is simply count them up. Like so. And that's the equivalent in streams. Now you might think, well, there's not much difference there between the two, and you're right, there isn't. We're not taking for loops away from you. But I would argue that this is actually more what and far less how, and we've upped the level of abstraction about what's going on. I can actually run that just to show you I'm not cheating here. Like so. Run it, we should get a number not very exciting out, but we actually get 94 out, okay? To show I'm not cheating, nothing under my sleeves here. So that's very simple. So what's going on here with this count method? What we have here, filter, is an intermediate operation. When we filter the list over the stream, it's not creating a new list. So it's not instantiating a new list and copying all the elements that are greater than 4 characters, strings greater than 4 characters in length. It's not creating a list. It's entirely lazy. And the work only happens when we do the count. We set up this recipe, and then we hit the count, we start actually doing a work. But count is actually made up of something else. If we look around and go into the implementation of count, it's made up of 2 further operations, which I'll copy and go back and paste in here. Like so, it's actually count is made up of a map and a sum. So what we do to actually count the number of elements we first map each element to 1, and then we sum up all the 1s. Now you'd think maybe when you're new to strings, you think, I can't do this type of thing. There's no way I can work it out. But if you transform your domain, sometimes you can do neat little tricks like this. Now if we look at sum, go into sum here, we see it's actually something called a reduce. So now what we get is, you might be familiar in other contexts, is filter, map, reduce. That's why I call it map reduce in the small. You can do it in the large and distributed as well. If we look at what's actually going on in a bit more detail here, I'll uncomment this. If I break it up into separate expressions, you wouldn't normally do this, but just for explanation purposes. First we get our words, then we get a stream of filtered words, then we get a stream of 1s, and then we get our count out here. So we build up this recipe, and then at the terminal operation of reduce, we do all the work. So we have two intermediate operations and 1 terminal operation and 1 source like that. You wouldn't normally do this, but it shows you how it's broken up. If I actually operate on the filtered words after I've called the map to long on it, I will get an exception. All you can get is a linear pipeline of streams. You can't branch, fork them, join them together. It's very, very simple. You get a legal state exception if you operate on a stream that's already been transformed. So it's essentially, streams is a lazy view of the elements covered by your source. There's definitely more what, less how. And the lambda expressions make this possible. If you were doing this with anonymous inner classes, it would just look awful. It would look terrible. It just balloon out like that. It really would not be a good way of doing this. If you've ever tried to use functional Java or anything like that with Guava, they have a little thing which says, please use these things carefully because it makes the Guava team weep when you overuse these anonymous inner classes. So lambdas is the way to go. We've pushed up the level of abstraction here. So now we can do stuff underneath the covers. Okay, let's look at something a little bit more different, but similar in here. Rather than count all the number of elements in the list, let's reduce all the strings to one big string instead, combine them all together. So we want to create a string of combined words, like so. We want to stream over it again, and we'll do the filter. So instead of doing a count, we want to actually create a large string, so we can do this. Like so. So that's going to add the strings together with a comma separated between them. Does anyone think that will work correctly? Does it look like it will work? Maybe? Will there be some problems? Shall we run it and see? Okay, well, we definitely get comma separated words here, but there's a problem. Do you see that? There's a rogue comma at the beginning. That's kind of crappy. We don't want that. So there's an alternative we can do here, is to have a one-argument reduction, but then we don't have a default value anymore. That empty string was our default value. I'll explain it a little bit more. It's not quite default. We no longer have a default value. What happens if this stream is empty? So we have to represent a stream using an optional instead. And an optional says, I have something or I don't have something. We're not using null as a value to say if it's empty or not, because we might have nulls in our streams. So we have this concept called optional, which you might, if you're familiar with Scala and languages like that, they all have optional and a lot more types of classes surrounding this. We've just added optional into Java SE8. And if a string is empty, we can chain a message like this onto it. So this should work as before, but we won't get the comment at the beginning now. That's quite good. If I change this so over 100 characters, there should be no words greater than 100 in Shakespeare, one hopes. We get an empty instead, like so. So you can use optional with care. Don't go and replace all things where you might return null with optional, like a hammer. I've got a new hammer. Everything looks like a nail when I see null now. Careful with it. Okay, so can anyone see any problems with that code? And it works. It looks quite nice. Is there anyone think of any issues that you might have with it? Performance, memory? So I think I heard it. It's going to create a lot of objects. Is that what the person said? Yeah, it's going to create lots of string objects. So that's actually pretty. It will suck in terms of performance and garbage collection and so forth like that. So this is Java. Things are mutable. So rather than a reduce, we have something called collect. And we can do this instead. Whoops. Excuse me. Like so. This is what you should be using unless you're doing things with primitive types and stuff like this. Reduce is very functionally orientated, but it's not really suitable for Java's mutable types and collections and strings and stuff like that. What you should be using is the collect operation. And there's a bunch of mechanisms you can do to say how you collect stuff together. So that will work as before. You don't have to worry about the empty string. You don't have to worry about optional. It will all do the things for you. Now, obviously, that printed out nothing because I had 100 in there, so let's drop it down to 4 and do it again. And then we get the data out. So rather than picking reduce, first go to collect and then see if you want to use reduce after that. There's a talk tomorrow on streams by Morris Natfalan, who will talk about this a lot more detail and collectors and so forth like that, but I'm not going to go into huge detail on this. So what was going on underneath the covers here? So the reason why it creates a lot of memory is it's like a sequential fold left. We're adding the empty string to the comma, to A, the first word, and then we're taking all that and we're doing the same again, and the same again, and the same again. That's going to create lots of garbage, whereas in the collect and joining, we use a string builder underneath the covers, so we can reduce the amount of garbage we actually do. So it's quite inefficient in Java. There's a bunch of stuff that you need to know about if you're going parallel, which I'll show later, but if you're using collect, you don't need to know about the fact that the reduction operation I have to pass in has to be associative, and the base value is not an initial value, but a special value. If you apply the base to a value, you get the same value out. So there's some rules here. The reason why we have those rules is if we do that, the implementation underneath the covers can do optimizations. So if we have those rules, we can start changing the grouping rather than all the way to the left, like in the above here. We can change the grouping so that we can group slightly differently. So we could group the A and the B together, or the C and the D, and then we can operate on those in parallel and then merge the intermediate results together. The associativity and the base value give us the wiggle room to distribute the problem out. So those are the key concepts, but most of the time when using collect, you don't need to worry about them. Okay, so let's do something else with streams. So we've got time. So I want to do a quick one using a bit more collect and showing some other APIs we connected up to streams. So I want to ask the question, in the book Ulysses, how many times does a word occur? So what we would want to hopefully get out of that is a map of a string, which is a word, and which is a key in the map, and the long, which will be the value of how many times a word has actually occurred. So first of all, we need to parse the text of Ulysses. So we're going to deal with a stream of string, which I'm going to call lines. And we're going to use a new method on files called lines, and we pass it the path to Ulysses, like so. And that will parse lazily the text file and pull out line by line by line every time we want to do something like that. But we don't want the lines here. We want to extract the words from the lines. So we need to operate on that stream of lines, create words out of it. So we use something called flat map. If you're in the monads talk or whatever monads done to us, you might know about flat map already. So we want to map the lines to words. So we can use another thing we've added to the API called splitters stream, like so. And that will essentially turn each line into a stream of words. So now we're dealing with a book of Ulysses as a stream of words. It's very, very concise with these methods we've added. And if you notice, the IDE is telling me something here that I could actually replace it with a method reference. So the IDE can actually help you sort of change the code around based on new features. Now you shouldn't, again, this is like a hammer. Everything looks like a nail. Use it wisely with judgment. Don't go replacing things just because the IDE tells you. Think of it as a hint that maybe you want to do it. But I'd argue in this case, using a method reference is actually more readable than using a lambda expression. So once we've got our words out, we can start doing some actual work on it. So we can use a simple filter, again, as before, just to filter out some noise. And now what we can do is we can do our collect, and this time we use a grouping by that Morris will talk about much more later. And what we want to do is our key in our map is our word, so it's essentially identity function, like that. And then we want to, for the same key, we want to increment a count. So what we do is we just do counting, like so. And that's it. We've actually got to assign it a value. So that's like so. And then we can actually print it out. So there's a new method on map called forEach that takes, you can do a lambda like so. Map will print it out if we just run that. We should get a map out. Okay, it's not sorted or anything. I'm going to skip the sorting bit because I'm going to run out of time. But you can see I've got the big map here. If you play around further, you can actually sort all these entries by the value if you want to get the most number of words. But I think if you look up Bloom, the character there, you should see that. Where is he? Bloom 279, he's the main character in the book, so that's what you'd expect. So it's very easy to use the IDE to play around and experiment with all this. You can do very concise problems very easily than if you're coding it imperatively. Okay, so let's go back to the slides. if I can actually get back to my slides. There we go. Okay, so hopefully that was a brief whirlwind introduction to streams and some other things we've added to the API. There are many types of stream sources. I showed them on collection. You can get them on arrays. There's int streams, there's files, as I showed, and you can roll your own with something more advanced called a splitterator, which is like an iterator on steroids, and it's the way we get our parallelism out from the sources. Now, stream sources manage a bunch of aspects. They access your elements. They're a way to decompose, and they have a bunch of characteristics, like am I sized? Like a list, array list, we know the size. Is it ordered? Yes, an array list is ordered. Is it distinct? No, a set is. Is it sorted? Set not, but a sorted set would be sorted. So stuff like that. And there's a bunch of characteristics you see here in this table we assign, and we use these characteristics to optimize the computation. And there are a bunch of intermediate operations, like I showed, like filter and flat map. They're lazy. They don't do any work usually, the stateless ones. For example, they have a bunch of characteristics how they manipulate the stream. I'll explain in a moment. And some parallelize or fuse better than others, like map or filter or flat map are stateless, but others, such as sorted or distinct, don't. They're stateless, stateful operations. So let's just have a look at what some operations do and how they affect the characteristics of the pipeline. So if we start with int stream range, it's sized, it's ordered, it's distinct, and it's also sorted. It goes 0, 1, 2, 3, 4, all the way up from end to end. If we do a filter, it removes the size, because a filter might remove an element from the actual stream. We don't know what its size is anymore, so the sized flag goes away. If we map, then we lose our distinct and sorted. If we say we're unordered, we lose our ordered flag. If we say we're distinct, we can inject distinct back into the stream. If we're sorted, we can inject sorted back into the stream. I'm going to skip limit. But you see, we keep track of these flags internally within the stream pipeline, so then we can do optimizations under the covers. And there's peek if you want to debug, which doesn't do anything. So there's a bunch of summary there from the table. So there's sources, intermediate operations, and then there's terminal operations. So invoking a terminal operation will execute the pipeline. And the terminal operation will take advantage of all those characteristics I talked about. So if we have a to array at the end, we can avoid copying for size pipelines by allocating a big array up front, because we know exactly what the size is. And there's a bunch of operations listed here and some notes and properties. So some of the rules of the games here, especially if you want to go parallel. So here's a little example I have. So I'm going through my words again. I'm streaming and I'm filtering it, and then I'm doing a for each. And what I'm doing in the for each is trying to add the word back to the list that I'm streaming over. What do you think will happen? I run forever until I run out of memory. Throw an exception? Maybe. We run it. Correct. What exception do you think it will throw? Okay, let's see. Should we take bets? So we got a concurrent modification exception. So we bath. We blow out. We've written it so that we can detect what's going on. It's the same thing if you iterate over an array list externally and you try and modify it while you're iterating, it will detect the same thing. So we try and detect errors like that. It's called fail fast, and we have a bunch of fail fast mechanisms in various sources to stop things like this happening. Now, this is a silly one, but I've been caught out by this in much more complex code, and it's actually saved me time debugging problems. So it was well worth the effort, I think, putting this in. So here's another one, and I'm jumping ahead of myself a little bit by going parallel, see if we can guess what's going to happen here. So I've got the same again. I've got a list here, FWS. I'm going to for each into it. So every element I get, I want to add it to the list like this. But I put a parallel on here, jumping ahead of myself for what it is. But what do you think will happen here? Is it going to produce the list correctly? It's going to be an exception. Is it going to form some malformed data? Let's see. So I get 93 there. Let's run it again. 94. Oh, there's a bit of non-determinism in there. Let's just remove that filter for a bit and then run it again so you get more data coming in. Oh, I got an exception. So what's happening here is that the for each is getting, as I go parallel, this is an 8-core system, the for each is getting called concurrently by threads. Every time an element is ready, it will call for each, so it's getting called by multiple threads, and I've got a concurrency issue, adding the elements to the list here. So what you could do is you could turn this into collections.synchronized. Oops, let me write that again. Connections.synchronized list, like so. And then it should actually work fine. There's actually a better way to do this instead. Let's just turn list, copy this out, and instead do like so. That's the way to do it, so that you can go parallel or sequential, you'll get the same result. So underneath the covers, it will work out what to do. So use for each with care. It has side effects. Okay, 24 minutes left. So here's a little bit more complex one. So I've got a stream, I'm going parallel. On the filter I'm doing, well, have I seen this word before? I'm asking in a set, have I seen this word before? If not, I'm going to do a side effect I'm going to call peak, and then call scene.add, and then I'm going to collect a to-list. So I'm doing the to-list correct, but I got some side effects going on in my peak operation. Do you think the set and the list will contain the same data, or will they be different? Do you think it will be distinct inside there? Let's have a quick look. Run it again. So they're slightly different. Be or not, to die, to fortune, they're different there. The reason is this is run in parallel. The filter and the peak are also run in parallel here, so we're going to get different data. The right thing to do if you want something distinct is to call a distinct operation, which will do the right thing. It's a stateful operation, which will do the right thing underneath the covers for you. So there's a way to do it with the existing operation. You don't have to monkey around with state inside the lambdas. Be careful with that if you want to go parallel. Okay, let's switch back to the slides. So I would describe that. So just to point out again, if you're going to use a for each or a peak, that's going to take something called a consumer, and it must operate by definition by side effects. So be careful when you use those operations if you want to go parallel. So why go parallel? There's really one reason why you'd want to do it, except just for pure fun, and that's to get your results faster. Maybe. That's the trick. There are many chips and cores. Let's keep them hot, but let's keep them hot efficiently. It's dead easy to keep the cores hot by doing something silly. We've got to do it efficiently. There's also, interestingly, lots of interesting work going on GPUs and that. And if you look at OpenJDK project Sumatra, they're actually working on trying to transform that stream pipeline and trying to execute it on a GPU where you've got many, many, many more cores than you would have on a normal machine like this. With 8 cores, I don't know how many cores my GPU has. But the key thing here is to not assume that parallel is always faster. We've made it really, really easy to do, but it's not necessarily the right thing to do. So it's a really sharp tool. Use it with care. And sometimes it will be slower than sequential. So you have to be careful. It's based on fork join. Fork join is pretty low level, so we've upped the level of abstraction. We use fork join underneath the covers to get the parallelism and control that we need. So it almost always takes more work to go parallel. And it's not a magic bullet. Again, parallel is not always faster. There's many factors which will affect performance. It can depend on your size, how your data decomposes. Are you dealing with a set or an array list? How many cores do you have? And what is the expense of the element going through the pipeline? Is it cheap or expensive? And there's cases like primitive streams for integers or boxing with ints. Boxing can affect performance as well. We've made it really, really explicit, but unobtrusive. It's just a parallel. Every stream that you define is sequential by default. And when you go parallel, underneath the covers, it will introduce non-determinism. But we've tried up top to retain the determinism so you get the same results going sequential and parallel. So let's have a quick look about what's going on underneath the covers. So I found quite an interesting way to describe what's going on by using the stream itself and producing a result out. So we got a primitive int stream here. The reason why we've added these is for performance, because boxing hurts. So I'm going to range over from 0 to 127 in integers. I'm going to go parallel. I'm going to box it. And then I'm going to group into a map where the key is the thread on which the integer was processed on. So I'm going to have a map of string to list of integer. So, and let's print out the result and see what we get. So it's sort of like peeking underneath the covers of what's going on here. So if you look at the results here, we see we got 1, 2, 3, 4, 5, 6, 7, 8 threads working using the fork join pool, the common pool. And if you notice, different threads have different lumps of work. And if you also notice, it always comes in sets of 4, not sets of 128 divided by 8. It's coming in sets of 4. So what's happening is we're over-provisioning the amount of work to try and balance out the lumpiness that goes on when we get different sets of work here. So you can, if you look under, you see here we've got 32, 33, 34, 35. Then it comes up. And then there's a big jump up to 100. Some other thread got the work from 40 to 43. So we're dealing up into little packets of 4 elements each into fork join tasks. And then we're saying, fork join, you work out how to execute these little things. And if I can try and do some ASCII art here, let's see if this will work. So just to get an idea of what's going on underneath the cover. So here's my sort of computation tree on the left-hand side of this, split out. I'm dealing with 4 leaf elements all the way up from 0 to 15, split up into 4 bits. And the first one gets executed on thread 1, second on thread 2, third on thread 2, and the fourth on thread 1. So what happens is on each leaf, we create a new map with the key and value in of the numbers. And then what we have to do is go up the tree and merge those values together. So we merge these 2 maps together like so, and then we merge all the way up like so. And we always merge the right into the left to preserve essentially the counter order of the int stream. So if you play around with this, and you can actually sort of quite easily look under the covers and see how the execution works without actually looking at the code. So ironically, if you're a web application, this is what all application servers should do by default, is disable parallelism, because your thread should be processing requests. What they shouldn't be doing is utilizing the CPU resources to execute streams in parallel. So this is what web applications should do. Most of the application servers should set this property to 0. And if they don't and you're having problems, this is what you should do underneath the cover. So if I set this system property to 0 and I execute this program, we see it all just comes out on 1 thread. Now, if you want to control the amount of threads that you're actually using, we don't have a mechanism to do that at the moment. All we have is parallel on the stream. We don't have a way of saying what the policy is at the moment. It's very on or off. But there's a hack, a sneaky hack, not necessarily supported, but if you really want to do it, you can. And that is to submit your stream on a fork join pool. And I can say my fork join pool is the size of 2, and I can submit my stream on that, because the way it internally works, it will pick up the context of where it's executed and run. So this one should run on just 2 threads, like so. So that's a hack to where you can control it until we work out a proper way to do it. Okay, back to the slides. Okay, so what I showed there is it's really, really greedy for parallel. That's what parallelism is. It will try and use as many resources at its disposal to try and go as fast as possible. We can't configure it at the moment. This is something we need to do in a future release of Java. We need to work out how to do this so you can better control it. I'm sort of speculating here. Perhaps rather than parallel sequential, if you say parallel under the covers, perhaps the runtime should work out whether to go parallel or sequential by measuring what's going on speculatively, sequentially, and then work out, well, I've got enough information here to say I'll try a speculative parallel execution and then see if it actually works out. And if it does, let's do it. And Hotspot is all about optimizing the runtime based on runtime information. It will inline methods and so forth. Perhaps we can do this. This is just me speculating. It sounds very simple, but I think there's probably some very hard problems to solve to get it right. So should you go parallel? Well, web applications, probably not, unless you really, really know what you're doing. There's a bunch of qualitative considerations you might need to know, like how good is the stream decomposition? Does it create a balanced tree of computation, or does it create a sort of write-heavy tree of computation? Is the terminal operation expensive or simple? Am I doing like a really expensive map merge or something like that? And what are the stream characteristics I talked about? If the stream is sized all the way through, you can usually get good performance out of it. But if you lose the size, perhaps not so much. There's a simple performance model you can sort of work out in your head with two pieces of data. One is if I know the size of my data, n, the number of elements in my stream, and I might know the cost of processing the element through that stream. So simple performance model might be n times q, approximate cost of the pipeline. So the larger n times q is, the higher the likelihood of good parallel performance. But it's really easy to know n, not quite so easy to know q. And this is the thing you might have to measure or build up an intuitive understanding of what it is. For small data sets, sequential usually wins, unless you've got a very, very high q. Simple pipelines are easier to guess at. Say, do you have 10K elements or more? Complex pipelines are harder to reason about. But the key thing here is, if in doubt, you need to measure in terms of performance. If you're in doubt, you need to measure what's going on, and that introduces other issues. Writing benchmarks is hard. There's all sorts of things that can interfere with your benchmarks. So use a benchmark tool, and there's a very good one called Java JMH, where M for me stands for micro, macro, or measurement. But it's really micro, but it's very broad and general. JMH is on the OpenJDK Code Tools project. It's nearing release 1. It's very, very good. Under the covers, it will work out what to do to try and protect you from what Hotspot might interfere with your measurements. It won't do everything. But it's very, very good, very easy to set up, annotation-driven tool, very, very nice. So let's look at some examples. So before I go there, I have a bunch of examples here. I'll probably get to the first two, and then we can have a vote on which one you want to see, because I'm running out of time. So I'm going to go through two extremes. I'm going to go for a low Q and a high Q. I suspect most people, when in their own problems, are going to be dealing somewhere in between those two. If you want to do this properly, I always switch off tiered compilation because it gets in the way. I also downclock my CPU to 2 gigahertz because often my chip is hyper-threaded, and that gets in the way. And a performance guy in Oracle told me, no one really knows how this works deeply around here, so turn it down, otherwise you get strange results. If you want to compare parallel with sequential, downclock your CPU if you got hyper-threading on there. That's what I'm told. Okay, so let's have a look at this one. So I've got a bunch of benchmark code here showing JMH. So let's have a look at the in-stream sum. This is the low Q one. So our baseline will be a loop where we loop over elements in an array, timesing them by 5 and creating a sum. So that's the equivalent parallel stream. arrays.stream, parallel, map, then sum, and then a sequential without the parallel. That is extremely simple. Intuitively, you can understand that that is a very simple operation. It doesn't cost very much. And we know the sum is a reduce, and it's just adding numbers together. That doesn't cost very much either. So intuitively, Q is quite low. So we might need quite a large n to actually get the parallel speed up. So let's have a look at the results on what I got on that. So here's my results, going from n all the way from 1 up to 1 million. And I have on the y-axis the speed up over the benchmark of the loop. So you can see the sequential stream in blue. After about maybe 1,000 elements, it gets close to the for loop. We still can't beat the for loop, unfortunately. Not yet, anyway. We need some more experts in hotspot runtime compiler to work on that. But if you notice, you get this S-curve for the parallel stream. The performance sucks. And then suddenly starts to get better around the 10,000 mark. The cost of splitting and merging data is high for lower number of elements because the queue is so low. So the cost, this fixed cost is very high and comes into measurement. But as we get more and more elements coming into the stream, we overcome that cost with the amount of work we have to do. And eventually, you overcome that and you get your parallel performance crossover around 10,000. And then when you reach 1 million elements, then you start to get the 2x speed up you'd expect on the laptop I use to measure this. There are some intricate details in actually measuring the performance here. I wonder if I should go into that very, very quickly. So if I measure this myself for 10,000 elements running JMH now, what JMH will do is run a bunch of warm-up iterations and then a bunch of measurement iterations. So you see here, it's doing a warm-up iteration to make things hot. And then it will do a bunch of iterations and measure. I'm doing this quickly. Normally you do it a lot more to get more data and average out. I just wanted to show something here. On 10,000, when I'm measuring this, it shows the sequential is actually slower than the parallel. That is not right. Something strange is going on here. Something strange is going on with hotspot. What you need to do is be careful when this method gets inlined after 10,000 iterations. It starts to affect the performance of the hot loop because we reach hotspot inline limits and it de-optimizes my hot loop. So you've got to be really careful when measuring simple pipelines, even with JMH. So this is something we have to improve in hotspot so that developers don't have to run into this. But at the moment, you have to increase your max inline levels if you're measuring simple pipelines. And then if I increased it up here, then I get what I would normally expect. A sequential is the same as a loop, and a parallel is slower for 10,000 elements. So just watch out for that. And if you can't remember what I say, but you know there's a problem, email me or email a list, and that will pop up. And if you want the code, I'll put the code somewhere so you can know you don't run into this issue, because I think a lot of people run into that. Okay, that's that one. Let's go back. So that's the low queue. Let's have a look at a different one, which is the high queue. Generating probable primes. So rather than do that, I'll just show you the code first. So how are we generating probable primes? So here's the baseline, which is the loop. So we're creating a list, a big integer, and we're creating n probable primes based on a certain bit length and a current thread local random, then adding it to the list and then returning it back. Not very complicated. You can do that like so in streams by ranging from 0 to n over int stream, going parallel, then mapping to the big integer, and then collecting to a list like so. Same problem, expressed slightly differently. Up the level of abstraction, we can go parallel now. And sequential is the same, but without the parallel op. Let's go back and have a look at the results. I'm not going to have time to go into a red one. That's showing a bug in my stream code I need to fix. But let's focus on the blue and the green. So now we look at the n from 1 to 1024. We see that at 4 elements, we immediately get the parallel speed up because the queue is so high, the n can be a lot lower. Creating probable primes is much more expensive operation, so we overcome the costs of going parallel and merging results because queue is so high. Does that make sense? Okay. Let's have a look. Right, I have 5 minutes, so we've got 4 others. The last one is not so interesting. Maybe the next 3, boxing, Monte Carlo calculation of pi, or megamorphic call sites. Who wants to see what? Who wants to see boxing? Put your hands up if you want to see boxing performance. Okay, 1. Monte Carlo calculation of pi. Okay. Megamorphic call sites. Okay, it looks like pi's 1. Let's see if I can do this in 3 minutes. So, this got my attention. How to calculate pi using a shotgun. I thought this is might be quite a fun way. Some physics guys, they fired a shotgun at a square piece of tinfoil, then counted all the pellets that hit the tinfoil that were in a circle and were outside the circle within the square. And they did that 200 times and calculated for deviations, wind speed, and stuff like that using some random sampling. And they could calculate pi from this. And the reason why they did that was in case there was a zombie apocalypse. And you would always have a shotgun around in a zombie apocalypse, so you could calculate pi. But we can also do it using streams. So that's essentially the algorithm here is you have a circle and you throw darts at the square and you calculate the darts in the square, and that's the algorithm there. It's very, very simple. And it's embarrassingly parallel. So let's have a quick look at the code. Okay, ignore the above bit. I just want to show you down here. I'm using something called splittable random, which is a new random number generated by Guy Steele, random number generated by Guy Steele and Doug Lee, the algorithm of which is also put into Fred local random. So we've now got a nice, better random number generator in the JDK. But here's the algorithm in parallel streams. What I want to do is I want to generate n pieces of data with a splittable random, and I want to filter based on this, the splittable random according to my thread. I want to get 2 doubles, the x and y position that my dart or my shotgun pellet landed. And then I want to return true or false whether it landed within the circle or outside the circle. And I want to count up all the times it landed within inside the circle. And then pi is essentially 4 times m over n. That's it. Embarrassingly parallel Monte Carlo algorithm. Very simple to express. So performance-wise, does this work out? There's also, you can do it filter count, or you can do it mapped along sum. Remember, count is composed of map and sum. In this one here, I'm reducing it slightly, so I can reduce the number of operations. Is there a difference in performance between those? Let's see. So just look at the blue with the filter. We see we get about a 2x speed up, but it's slower than the baseline loop. But if we use the map instead, we still get the 2x, but it's actually better increase. The more operations you add to the stream, the more work it has to do, the harder hotspot has to work to optimize as well. So we get the speed up, but also be careful sometimes if you really want to go really, really fast compared to the loops, be careful of what intermediate operations you add to it. And that was over 2 to the 24 samples to get not a very accurate representation of pi. So at the zombie apocalypse, if you calculate pi using that, it's pretty poor. There probably is far better ways. Okay, so quick summary, 1 minute. So hopefully you've got an idea that what we've added to 8 is quite a powerful framework. You can, when you're doing bulk operations or aggregate operations in your data, you can create more compact, readable, hopefully more performant, less error-prone code. I think the basic thing is to focus on writing good, clean code and then worrying about performance later. And I think streams allow you to do that better. And then if you've got a performance issue, measure and identify your hotspots. It's an easy path to parallelism, but not always the right thing to do. It's deeply integrated in connections, and There's lots more optimizations in the future we can do, and I hope we're going to do. I'm very excited about value types in the future. I think those will have some very interesting optimizations for streams, hopefully. And that's it. I've got 1 minute left, and probably no time for questions, but you can come and ask me afterwards. Okay, thank you.